Now, we're going to use those three observations to give a bound for this sum. Based on the observations above, we'll divide this sum into two categories based on the properties of the indices I sub 1 through I sub k. Specifically, we'll consider the following two categories. First, the odd part. By this we mean at least one of the indices I1 through Ik occurs an odd number of times. And by our discussion, the summand will be bounded by this. And the number of terms here will be trivially bounded by m raised to power k. So this part is less than or equal to times m to the kth power. The second category is what we call non-odd part. This part refers to the case when this does not happen. Namely, none of the indices I1 through Ik occurs an odd number of times. And each individual term will be trivially bounded by 1 for that part. So this will be less than or equal to 1 times the number of k tuples with none of I sub j occurs an odd number of times. So this will be the bound for this part. And this guy will be bounded by the sum of these two. So now the question is, what is the size of this number? Question. How many tuples I1 through Ik where I1 through Ik are all between 1 and m are there of the form that none of I1 through Ik occurs an odd number of times. The precise number may be hard to find, but we are happy with a good upper bound or a good upper bound. And now we'll start with our counting. The counting is as follows. Read I1 through Ik from left to right. There will be two cases. For each j in 1, 2 through k, Ij is either fresh What do we mean by fresh? Fresh means ij is not equal to any of I1 through ij minus 1. So we are reading from left to right. So we are looking at for each ij if it is equal to any of I1 through ij. The fresh case means it is not equal to any of those j minus 1 terms. It's the new one. Or a repeat. This means it is equal to one of them. Or I should say at least one of. So there are two cases. For the first case, now we are interested to know how many choices we're going to have for each of those two cases. For the first case, the fresh case, the estimate is that we're going to have at most m choices, since I sub j is greater or equal to 1, less than or equal to m. This is a rather trivial bound. And for the second case, we're going to have at most k choices. At most k choices for I sub j, because this is a repeat of the first j minus 1 terms. And there are at most I1 through ik k terms. So j will have at most k choices to the end. Okay. Those are the cases for I sub j. We are also interested to know how many tuples I1 through ik could fall into those two cases. Now we are going to bound this number with our fresh or repeat counting. Now since none of I1 through ik occurs an odd number of times, for this category, since none of I1 through ik occurs an odd number of times, in particular, none of them occurs precisely one time. At most, half k. Remember, k is even. At most, 1/2 of the k of the cases are fresh. If you like, you can prove this more rigorously. Suppose there were k divided by 2 plus 1 many j's with ij fresh, then some ij with j between 1 and k will occur only once. In the set j1, j2 through jk, which will lead to a contradiction to the assumption that none of them occur precisely once. Why will this happen? This is because if there are more than half many j's with ij fresh, then the rest of them will be less than half, which means they will not be able to cover all those more than half many fresh edges. By the pigeonhole principle, or whatever basic combinatorics, you know that some ij have to appear precisely once, which will lead to the contradiction to this assumption. Okay, now, so once it is decided which numbers I sub j are fresh or repeat for I greater or equal to 1 less than or equal to k, there are at most, I'll put the underline here to be, this is a blank to be filled in. There are at most this many remaining choices to be made. So first notice that the decision on how many numbers I sub j are fresh and how many of them are repeat, the choices here will be at most 2 raised to the power k. 2 times 2 times 2, there will be k choices because we are looking at I1 through ik, k terms. Once this is decided, now look at this. We have concluded that at most k divided by 2 of the cases are fresh. And from the above, we know that in fresh cases, ij will have at most m choices. So we would expect the worst case scenario is that there will be m raised to the power k divided by 2 times, noticing that the remaining cases are repeats. So ij's are repeats, which will correspond to at most k choices. So which will correspond to k raised to the power k divided by 2 many choices. This part is fresh, and this part is repeat. Here, some of you may have already noticed that we have already implicitly used an additional assumption. This additional assumption that m is greater or equal to k. But at this moment, we are not very sure why m can be greater or equal to k. We will justify this assumption later with our choice of k. We have to finalize our choice of k in the end. Anyway, you will see. To summarize what we have done, we have shown that this number is bounded by, now we multiply those three things together, this is what we get. Now we are ready to finish the proof of this corollary. This guy will be bounded by two parts. We have already found an estimate for this. So last term will be less than or equal to there will be two parts. The first part is and the second part is, and I will show you this estimate will be good enough for our purpose to bound this. Noticing that m raised to the power k cancels with m raised to the power k. Simplifying this, we get previously this is a function of m and x, which goes to 0 when x goes to infinity. Now, when we integrate this epsilon raised to the power k to here, there will be two new variables. This is the first part. The second part, remember at the beginning I said this k is a large even number to be optimized later. This k appeared in this application of Chebyshev's inequality. It's an exponent for the higher moments. And here is how we optimize in k. Now we optimize in k by choosing k to be the largest even integer less than so we have a lot of freedom in choosing this, but I think epsilon squared times m divided by 10 is enough. When you make this choice, then it follows that it's 4k divided by epsilon squared times m raised to the power k divided by 2 will be less than or equal to, noticing that this guy will be monotonically increasing with k. And let's simplify this. Here we flip this base and pull out a negative sign in the exponent. This is what we get. The point is, this number is greater than 1. So this guy is exponentially decaying in m. Now, comparing this with what we want to prove. What we want to prove is this. It's very close. This term will be less than or equal to constant c times exp of negative epsilon squared m divided by c for some carefully chosen constant c. If you make this c large enough, because this part is monotonically increasing with c. And now we have chosen this k to be a larger even number less than this guy. If epsilon is small, or if epsilon is not too big, the k must be less than m, which guarantees our additional assumption that m is greater or equal to k. So this assumption is guaranteed by our choice of k. So we are good. And now this k depends on m. We can remove this k as a variable here. We get this guy less than or equal to, and we are done, finally.